Hello students. In this video segment we will cover two sections, section 10.3 polar coordinates and section 10.4 areas in polar coordinates. Section 10.3 is intended as a review of polar coordinates from Trig, and I decided to cover both of the sections 10.3 and 10.4 simultaneously. So in this section you'll see an extremely brief review of polar coordinates, and then we'll integrate, no pun intended, areas from calculus in polar coordinates. Okay, so as a very brief review of polar coordinates, I'd like you to recall that polar coordinates gives us just another way to represent points in the xy plane. So let's assume we have a point in the xy plane, and the point in rectangular coordinates is given by x and y. Okay, where x and y are as pictured. In polar coordinates, we don't state an x and a y. We state a value for r, and I almost said distance because it looks like r should be a distance, but it's really a displacement. More on that in a minute. And we state an angle theta pictured in standard position. So we could either state rectangular coordinates x and y, or we could state polar coordinates r and theta. Okay, so for example, suppose I want to sketch the point in the polar plane given by 3 and pi over 4. What I'm going to do is I'm going to show you the way I suggest to my trig students to sketch points in the polar plane. To sketch the point 3 comma pi over 4, I suggest that you first consider the second polar coordinate, the pi over 4. And imagine rotating the entire x-axis through an angle of pi over 4, or a copy of the x-axis through the angle pi over 4. So if you imagine rotating the x-axis through an angle of pi over 4, the positive x-axis will now be shooting through the middle of quadrant 1, and then along that rotated x-axis move 3 units. So here's x equals 1, x equals 2, x equals 3. So along the rotated x-axis we would move 3 units, and then mark off the point corresponding to r equals 3 and x equals theta equals pi over 4. So r in this case is a distance from the origin of 3 units. So I didn't call r a distance, though. I called r a displacement. So for our second example, suppose we want to sketch the point in polar form given by -3 and let's say 3 pi over 4. -3 and 3 pi over 4. So just as before, imagine rotating a copy of the x-axis through an angle of 3 pi over 4. So let's do that. Let's see. So here's the polar plane or rectangular plane, and imagine rotating the x-axis through an angle of 3 pi over 4. So the positive x-axis before rotation was in its usual position. If we rotate a copy of the x-axis through an angle of 3 pi over 4, the positive x-axis, if you will be pushing through the second quadrant. So if we mark off along the original x-axis the coordinates or the numbers 1, 2, and 3, then those numbers get moved into quadrant 2 as well. So here's again a copy of the x-axis in quadrant 2, and let's mark off the negative coordinates along that rotated x-axis, -1, -2, -3. So the point corresponding to -3 and 3 pi over 4 is not in quadrant 2 where the angle is. It's actually in quadrant 4. So this is the reason why I say that r is not a distance. It's more of a displacement. A displacement can allow for negative values. So really, the r can be viewed as either a displacement or a coordinate along the rotated x-axis through the angle of whatever theta is, in this case 3 pi over 4. So let's go back to our original point. The original point was, the first point was 3 and pi over 4. Let's consider that point, but let's also consider the point -3 and 5 pi over 4. So our original point was 3 and pi over 4. So our original point, wait a second, I'm still getting used to this magic pen. The original point was 3 and pi over 4, so we rotated the x-axis, or a copy of the x-axis, through an angle of pi over 4. And then, and then along that rotated x-axis, we move 3 units. So 1, 2, 3, where the old 1, 2, and 3 were as pictured, and we plot the point. So 1, 2, 3. When you actually do this, you don't have to write out the coordinates along the rotated x-axis. Let's consider the new point, -3 and 5 pi over 4. Okay, so let's do that. Let's consider the new point, -3 and 5 pi over 4. So imagine rotating the x-axis through an angle of 5 pi over 4. Well, 5 pi over 4 shoots right through, gets us our x-axis shooting right through quadrant 3. So the angle 5 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 rotates our x-axis through quadrant 3. So the positive x-axis used to be pointing in its original direction. Now the positive x-axis is pointing through quadrant 3. So the coordinate 3 along the x-axis would look like right there through in quadrant 3. So -3 would put us back into quadrant 1. So -1, -2, -3, and our point would be located in exactly the same position as the point 3 and pi over 4. Our original point was 3 and pi over 4. So what we get out of this is that if you want to identify the location of a point in polar form that has a negative value for r, you can immediately say that it's going to be in the quadrant opposite the quadrant theta across the origin. So the angle theta in our last example here was 5 pi over 4 in quadrant 3. Opposite that across the origin would put us into quadrant 1. If the r value is positive, then the actual location of the point is in the same quadrant that theta is. So the original point 3 and pi over 4. Pi over 4 is in quadrant 1. So 3 comma pi over 4 will be located in quadrant 1. The second thing we see from this is that points in the polar plane, or points with polar representations, don't have unique representations. This point, 3 comma pi over 4 and -3 comma 5 pi over 4 are the same point. They just have different representations in polar form. Okay, so there's a review of graphing points in the polar plane. Now let's look at, let's say, converting from rectangular to polar and vice versa. So let's imagine the idea of, or let's review the idea of converting from polar to rectangular and rectangular to polar. So here's here's a point in the xy plane, or in the plane, which we're also going to view as a point in the polar plane. So let's put all four quantities in the same picture. So this is the point represented by coordinates x and y. It's also the point represented by polar coordinates r and theta. So there are all four of the variables. Let's find four relationships with these variables that allow us to convert from one system to the next. Oops, I'm trying to get that stray mark here. Bear with me. Still getting used to this. There. All that effort just to get a dot out of the picture. Okay, so let's take a look at the relationships between r and theta and x and y. Specifically, let's look at a relationship that allows us to go from polar to rectangular form. Polar to rectangular form. That means if I give you an r and a theta, you should be able to give me an x and a y. Well, notice that from trig we have x over r equals cosine of theta, and y over r equals sine of theta. So if I gave you an r and a theta, you could tell me that x then equals, by multiplying both sides of the first equation by r cosine theta. And similarly, if you multiply the second equation by r, you get y equals r sine theta. So these two equations allow us to convert from polar to rectangular. So if I wanted to convert from polar to rectangular, the equations that would do it are x equals r cosine theta and y equals r sine theta. Okay, so suppose I wanted to convert the other way. Suppose I wanted to convert from rectangular to polar. Suppose I wanted to convert from rectangular to polar. So let's do that next. Rectangular to polar. That means I give you x and y, and you come up with r and theta. So let's find a relationship, and they're very easy relationships between the four quantities that allow us to given x and y, find r and theta. So first, let's find a relationship between r and x and y. It's pretty clear that the Pythagorean theorem holds true. So r squared equals x squared plus y squared. So if you give me, or if I give you an x and a y, you can give me an r simply by substituting x and y into that equation. I'm not going to solve for r because, remember, r can possibly be positive or negative. So if you wanted a positive value for r, you would take the positive square root. Negative value for r, take the negative square root. So now let's find a relationship that would give us theta given x and y. So given x and y, I want theta. So what's a relationship between x and y and theta? The hint is it's from trig. It's one of the 6 trig functions, x and y and theta. The relationship is that tangent of theta equals y over x. And again, here I'm not going to solve for theta because it's possible to give all kinds of different values for theta. For example, if one value of theta equals pi over 4 would work, you could add 2 pi, one whole revolution to that, and you would still have the same location, the same point. So the relationship that solves for theta is not given in terms of theta; it's given in terms of tangent theta. Let's use these 4 relationships to do a couple of problems. So just to kind of highlight where we are at this point, in red are the relationships between R and theta and X and Y that go from polar to rectangular. In green are the relationships between the four quantities that go from rectangular to polar. So as an example, as a real quick example here, convert to, let's say, rectangular form. Rectangular. And the point is 2 and pi over 4. No, let's do a little more interesting angle than pi over 4. Let's do 2 and let's say 4 pi over 3. This is the point in polar form. So that we're given this is our R and our theta. So the red relationships give us the conversion from polar to rectangular. So x equals r cosine of theta and y equals r sine of theta. So x equals r cosine theta and y equals r sine of theta. Okay, so to finish this off, we simply compute the cosine and sine of 4 pi over 3. 4 pi over 3 is in quadrant 3. 4 pi over 3 is in quadrant 3. In quadrant 3, both sine and cosine are negative. So the cosine of 4 pi over 3 is the opposite of the cosine of 1 pi over 3. And the cosine of 1 pi over 3 is 1/2. Also, the sine of 4 pi over 3, since 4 pi over 3 is in quadrant 3, the sine is negative. So the sine of 4 pi over 3 is the opposite of the sine of 1 pi over 3. You could also get these values using the unit circle. So however you get them. Then the solution then, the answer is that the rectangular coordinates then are -1 and negative radical 3. Okay, let's do one more before we head towards some calculus. Let's convert from rectangular to polar. So convert, what is the same wording? Convert to polar form. And let's say the point is x, y equals -1 and radical 3. So it looks real similar to the point we just solved for in the last example. -1 and radical 3. Okay, I'm interested in finding r and theta. So remember that the green relationships give us a conversion from rectangular back to polar, or rectangular into polar. So r squared equals x squared plus y squared, and tangent theta equals y over x. R squared equals x squared plus y squared. So r squared equals 1 plus 3r squared equals 4. And since we're not specifically asked to find a negative value for r, just choose the positive square root. So r is 2. Finding theta is a little more complicated. In fact, this is the hardest part about converting from one system to the other, is finding theta. The tangent of theta equals y over x, radical 3 over -1. So that tells us that the tangent of theta equals negative radical 3. We can't use our calculator to get a solution out of this. The calculator is programmed for inverse tangents. Actually, the calculator is programmed with the domain of the inverse tangent, and the inverse tangent is between negative pi over 2 and pi over 2. Okay, so the inverse tangent lies between negative pi over 2 and pi over 2. So if we were to use the calculator to find the inverse tangent of negative radical 3, we would get negative 60 degrees, and this is wrong. So we have to do a bit of a reality check on this. So the point, in order to do this, you might want to consider graphing the actual point itself. I'm going to clean this up just a little bit. You might want to consider graphing the point itself. So here's the point, negative 1, negative 1, and radical 3. Negative 1, radical 3 is in quadrant 2. So the angle that we need to get out of this for our theta has to be a quadrant 2 answer to this, or solution to this equation. Well, if you ignore the radical 3, the tangent, I'm sorry, if you don't ignore the radical 3, if you ignore the negative, the tangent of pi over 3 is radical 3. So a quadrant 1 answer would be pi over 3. How did I get that? I have the unit circle memorized. So from the unit circle, you can see that the tangent of pi over 3 is radical 3. But our answer has to be in quadrant 2. That pi over 3 can be regarded as what's called the reference angle for our answer. So our actual answer needs to be the quadrant 2 answer, pi minus pi over 3, or 2 pi over 3. This we could have gotten, I referred to the unit circle, but we could have gotten this immediately just by looking at the unit circle. The angle in quadrant 2 that has a tangent equal to negative radical 3 is in fact 2 pi over 3. So our answer is, that R and theta equal 2 and 2 pi over 3. Okay. All right. So now for the remainder of our lesson today, or our section today, our 2 sections today, I want to combine a review of graphing equations in polar form with some calculus, finding the area captured by equations in polar form. Okay. So here's our first example. It's kind of a simple one. For example, suppose I want to find the area enclosed by a curve given in polar form. So suppose I want to find the area, let me clean this up a little, find the area enclosed by the equation R equals 3. Okay, so in order to do this, I need a couple of things. So from geometry, or rather from trig, and from the review of trig and pre-calc, I need a graph of R equals 3. Well, R equals 3, imagine graphing every point in the polar plane that has an R value of 3. So regardless of theta equals 0, theta equals pi over 4, theta equals negative pi over 6, R has to shoot out 3 units from the origin. And when we do that, we generate a circle. So if we do that, we generate, in fact, a circle. Okay, this circle looks kind of lopsided here. Let's see if I can get my pen to graph a circle for us. Let's see. Let's see. I guess I don't need to obsess too much here. Close enough. All right. So here is a circle, and let's put this circle in the xy plane, or in the polar plane. Let's put this, see if I can center this thing. I'm sure there's a more efficient way to do this. Okay, so here's a circle in the polar plane, and notice that the R value is always 3. For every point on this circle, the r value is 3. Theta can take it on any value. There's no mention of theta in this equation. So as long as we put as our first coordinate 3, as long as we put our first coordinate as 3, theta can equal any value, and what we sweep out is a circle. Okay, so r equals a constant gives us a circle in the polar plane. So what I'd like to do is to find the area of that circle, and I don't want to do it by geometry. We have a formula that says that the area of a circle is pi r squared. I want to do this using calculus. So this is how we do this. Here's our circle. Here's our circle, and I'm going to put this is our circle in the polar plane. What we do is we imagine we're going to do the same thing that we do to get the area of a region in calculus 1. We're in calculus 1, we consider in calculus 1 we consider finding the area by dividing the area into an infinite number of rectangles and then summing up those individual areas by using integration. We do the same thing in polar coordinates, but we don't divide up the circle in this case into rectangles. We divide up the circle into an infinite number of little circular wedges. Okay, so here's supposed to be an infinitely small circular wedge. So let's give this circular wedge some dimensions. We're going to give it a radius r, and we're also going to give it a small angle d theta. Okay, I want to find the area of that one circular sector, and I'm going to add up the areas by using integration. Okay, so we're going to need something from geometry. From geometry, we're going to need a formula for the area of a sector of a circle. So from geometry, we're going to need the area of a sector of a circle. So here's a sector of a circle. Here's what I mean by sector of a circle. Suppose we have a circle of radius r, and we have a portion of the circle which we call a sector of a circle corresponding to the angle theta. From geometry, we know that the area of that sector suddenly my geometry tool is working here when I don't want it to work. Okay, from geometry, the area of a sector of a circle is given by area equals 1/2 r squared d theta. You don't have to remember, we don't have to worry about deriving that, but we do need to use it. So back to our infinitely small sector from our circle, the one we're considering. The area, the infinitely small area, or the area of that circular element is 1/2 r squared d theta. For our circle, the area, or the radius of the circle is 3. So the area of that one sector of our circle of radius 3 is 1/2 3 squared d theta. Total area we get by summing up all the areas of those sectors, and we sum up those infinitely small sectors by integrating the sectors from 0 to 2 pi. We're integrating with respect to theta, and theta varies between 0 and 2 pi. This integral is very simple. 3 squared is 9, times 1/2 is 9/2. So we're integrating really 0 to 2 pi, the integral of 1 with respect to theta. The antiderivative of 1 with respect to theta is theta, from 0 to 2 pi. And this gives us then 9/2 times 2 pi, or 9 pi square units. Which coincides exactly with what we'd expect. The area of a circle we know from geometry is pi r squared. The radius is 3, so it's pi times 3 squared, or 9 pi square units. Okay, let's take a look at a substantially more involved problem. Let's take a look at finding the area enclosed by something a little more involved. I want to find the area enclosed by r equals 4 times 1 plus cosine of theta. Okay. Most of our work with this is going to be involved in actually reviewing a sketch of the curve. I'm going to review how I suggest to my trig students to sketch polar equations. So if you remember a different way to do this, use your way. But we do need to be able to graph polar equations by hand. You can always verify your graphs by using a calculator, but we need to be able to graph polar equations by hand. So what I do is I suggest to my students in trig that they graph the polar equation in the rectangular plane, the way they're familiar with graphing. So let's distribute the 4 in this equation. So we're looking at 4 plus 4 cosine of theta, or if we reverse or rewrite the equation with the cosine term first, we're looking at 4 cosine theta plus 4. And let's graph this in the rectangular plane, not using the variables x and y, but still using the variables r and theta. So here's our rectangular plane, but the variables are not x and y. The variables are r and theta. So the equation 4 cosine theta plus 4 is nothing more than the graph of 4 cosine theta shifted up by 4. Okay, so if I graph one period of the cosine function very briefly, remember, looks like this. Shift that graph up 4 units. Well, if it were 4 cosine theta, the amplitude would be 4. If we shift this up by 4 units, our graph will then look something like this. So this is the graph of one period of 4 cosine theta plus 4. Oops, this is not correct. The period of the function is not 4. Period of the function is 2 pi. Okay, but the amplitude is 4. So this is okay. So the points along the x-axis that are important for us are 2 pi, 1 pi, pi over 2, and 3 pi over 2. Okay, now we're going to use this graph, the graph of the equation 4 cosine theta plus 4 in the rectangular plane with r versus theta, to graph our graph in the polar plane. And we're going to do it in a very efficient manner. So imagine now graphing in the polar plane. In the polar plane, the r values don't go up and down the way the y values do in the rectangular plane. The r values shoot out of the origin. They shoot from the origin radially outward. So what I'm going to do is I'm going to graph the curve r equals 4 cosine theta plus 4 in the polar plane by looking at the graph that I've graphed, looking at the graph of the same function in the rectangular plane. And I'm going to go quadrant by quadrant. Okay. So I'm going to, in the polar plane, I'm going to graph first in quadrant 1. In quadrant 1, the angle varies, and the angles vary between 0 and pi over 2 for points in the polar plane. Now look at the graph between 0 and pi over 2 in the rectangular plane. In the rectangular plane, as theta varies between 0 and pi over 2, the r values vary from 4, and they get smaller and smaller and smaller and smaller, smaller and smaller until they reach an r value of 2. Those values that go up are placed in the polar plane from the origin going out. So specifically, that first red arrow that I drew along the r-axis would be placed horizontally when theta equals 0 in the polar plane. So in the polar plane, that r value of 4 would be placed shooting outward from the origin, corresponding to an angle of 0. That last red arrow that I drew, the red arrow in the rectangular version of this graph at pi over 2, is 2 units long, and it's going vertical in the rectangular plane. In the polar plane, it's also going vertical, but only because the angle that corresponds to that arrow is pi over 2, and that pi over 2 is 90 degrees. So the first arrow, the horizontal arrow, corresponds to theta equals 0, and the second arrow corresponds to theta equals pi over 2. And now we put the rest of the arrows in. As theta varies between 0 and pi over 2, look at those arrows. They start at a length of 4 and get smaller and smaller and smaller until they reach arrows of length 2. So I'm going to put those same arrows in the rectangular plane. I'm going to put them in the polar plane. They're getting smaller and smaller and smaller as we increase the angle theta from 0 to pi over 2. Okay. I'm going to do the same thing in quadrant 2. In quadrant, except I'm going to switch to, let's say, green. In quadrant 2, the angle varies in the polar plane between pi over 2 and pi. Now let's look at the rectangular graph. In the rectangular graph, as theta varies from pi over 2 to pi, the r values continue to decrease from from 2 and get smaller and smaller and smaller and smaller until they hit a value or a length of 0, or an r value of 0. Those same green arrows get plotted in the polar plane, but shooting out from the origin as theta varies between pi over 2 and pi. So those same arrows, those same green arrows, get placed in the polar plane, but they now shoot out from the origin and get smaller and smaller and smaller. Okay. If we continue on in quadrant 3, the angle in the polar plane varies between pi and 3 pi over 2 in quadrant 3, but in the rectangular plane, horizontally, the r values increase from 0. I'm graphing in blue now. They increase from 0 to 2. So those arrows, those R values in the rectangular plane that are going vertically, shoot out from the origin in the polar plane. Those same arrows increase in size from 0 and get larger and larger and larger and larger until they reach a length of 2 at 3 pi over 2. Okay, I'm going to switch, let's say, to black to graph the arrows in quadrant 4. In quadrant 4, in the rectangular plane, R varies from 3 pi over 2 to 2 pi horizontally, and the R values get bigger. They start at 2 where we left off and get bigger and bigger and bigger until at 2 pi the R values reach 4 in length. So just as before, we put those black arrows in the polar plane, but shooting out from the origin. Those R values are going to get bigger and bigger and bigger and bigger and bigger as the angle varies between 3 pi over 2 and 2 pi. If we connect the tips of all of those arrows in the polar plane, we get a graph of our polar function. We get a graph of our polar function. If we connect the tips of all those points in the polar plane, kind of missed on that one, we get a graph of our function in the polar plane. Now this is the technique I use for my trig students. If this technique doesn't work for you, if you have a better technique, then use it. The only technique that we really can't rely on is our calculator. A calculator can help us with these images. In fact, the calculator can really produce some nice images. But what we're going to need are actual angles that correspond to specific points in the polar plane. We're going to need to be able to work with our graphs by hand. So I suggest that you practice graphing some of these polar equations, or all of them if possible, by hand. Okay, so now let's go to the calculus portion of this problem. The original question wasn't the original problem wasn't to graph the equation in the polar plane, although we need its graph. The original problem was to find the area. So what we're going to do is pretty much the same thing as we did to find the area of a circle. I'd like to get, before we do that, to get an image of our graph of this curve. So give me a second to draw this graph. We kind of need this curve from scratch. So here's our curve. In trig we call this a cardioid. Cardio means heart, and so this is sort of heart-shaped. And this is the graph of a little bigger picture of our graph of r equals 4 times 1 plus cosine of theta. So to get the area of this region, I'm going to imagine filling this region with an infinite number of really thin circular sectors that are pieces of a circle. And I'm going to draw a typical one. A typical circular sector would look like this, let's say in red. A typical circular sector would look like this. So imagine filling our curve with an infinite number of little circular sectors. The circular sectors will vary in size as we move from part to part of this area. So another circular sector would be out here. It would have an entirely different radius. But each of these sectors that I've drawn are in fact sectors of a circle. So here's another one. So we imagine filling our region entirely with a whole bunch of these, infinite number of these circular sectors. Let's give the circular sectors some dimension. So this is the first circular sector I drew in the first quadrant would have a radius r and would correspond to an infinitely small change in angle, let's say d theta. And from geometry, we know that the area of a circular sector is 1/2 r squared d theta. So the area enclosed by the cardioid, the entire area, is 1/2 r squared, the integral of 1/2 r squared d theta, as theta varies from 0 to 2 pi. So this is the formula for the area of this cardioid, but we can't integrate this. We're integrating r squared with respect to a different value theta. So we substitute the function, the specific polar function, into our integral, and that means we're integrating from 0 to 2 pi 1/2 4 times 1 plus cosine of theta, 1/2 r, 4 times 1 plus cosine theta, squared d theta. So the integrals that arise in this section, the integrals are going to involve something very simple from our past. Most of the integrals are involve the powers of sines and cosines. So I'm going to perform the integration on this problem. In general, for the remainder of the lecture, I'm just going to set up the integrals, and it's up to you guys to evaluate the integrals, since you're experts at integration by now. Okay, so let's continue this. Let's find the value of this integral. So this is the integral from 0 to 2 pi. I'm going to square out the 4 in the brackets. So I get 16 multiplied by 1/2. That gives me 8, which I can pull outside of my integral sign. Then I'm going to FOIL out the 1 plus cosine theta to get 1 plus 2 cosine theta plus cosine squared theta, integrating with respect to theta. Okay. The first two terms in this integral are very simple. The integral of 1 is theta. The integral of cosine, 2 cosine, is 2 sine. How do we integrate cosine squared? How do we integrate even powers of sines and cosines? If you recall, we integrate even powers of sines and cosines by using power-reducing formulas. So the power-reducing formula for cosine squared says we get 1/2 times 1 plus cosine of 2 theta. So 1/2 plus 1/2 cosine of 2 theta. Integrate with respect to theta. I think I'll combine inside in the integrand the 1 and the 1/2 to give me 3/2. So 3/2 plus 2 cosine theta plus 1/2 cosine 2 theta. Integrate with respect to theta, and the integral is very simple now. The integral, or an antiderivative of 3/2 is 3/2 theta with respect to theta. Integral of cosine is sine, 2 sine theta. Integral of cosine 2 theta is 1/2 sine 2 theta, but there's already a half as a factor there, so 1/4 sine 2 theta. All this is carried between 0 and 2 pi. Okay. What's kind of nice here is at the lower limit of integration, none of the 3 terms in this antiderivative give us any non-zero. All the 3 terms give us 0. Theta is 0 is 0, sine of 0 is 0, and sine of 2 times 0 is 0. In fact, at the upper limit of integration, sine of theta and sine of 2 theta are both equal to 0. So the only thing that's going to give us a contribution, non-zero contribution to this area is the upper limit, and it's going to be the upper limit at 3/2 theta evaluated at the upper limit. So the area then is 8 times 3/2 times 2 theta, or 2 pi rather, and this gives us 24 pi square units. Square units, since we're looking at area. Okay. So before we look at our next example, let's look at developing a simple formula for areas enclosed by a polar equation, a general formula. So let R equal f of theta be a curve in polar form. And suppose I'm interested in finding the area enclosed by f of theta for theta between two values. Suppose I'm interested in finding the area enclosed. Let me try that again. By the curve between two angles. Suppose that's this line corresponds to the angle alpha. This line corresponds to the angle beta, and this is a graph of the curve r equals some function of theta. So this line corresponds to theta equals alpha. This line corresponds to theta equals a constant beta. And I'm interested in the area enclosed by this region. What we do is, to develop the formulas, we assume that we fill the region with an infinite number of little circular sectors. My smart pen is being too smart here. So here's one of those circular sectors. Let's give the circular sector some dimensions. So r is the radius of the circular sector, and this is the infinitely small change in theta. We know from geometry that the area of the one circular sector, dA, equals 1/2 r squared d theta. So the total area then becomes the sum of the areas of the little sectors. So we sum up differential elements of area by integrating them, and for our particular area we integrate between theta equals alpha and theta equals beta. And just as before, we can't integrate this directly because we're integrating r squared with respect to theta, so we substitute our specific function, our polar function, into the integral. And we get our first general formula for the area captured within a polar by a polar equation in between two angles, theta equals alpha and theta equals beta. Okay, so let's take a look at another example. So for our next example, let's find another area. So for example, find the area enclosed. Find the area enclosed by r equals sine of theta. R equals sine of theta. I'm going to use the technique that I used to graph our last polar equation. So I'm going to first consider the graph of r equals sine of theta in the rectangular plane. So let's graph one complete period of r equals sine of theta. Okay, give me a second here. That's better. Okay, r equals sine of theta looks like this in the rectangular plane. So we're graphing this in the rectangular plane, r versus theta. So one period of the sine function is between 0 and 2 pi. Pi over 2, 3 pi over 2. I'm going to then graph the corresponding function in the polar plane. I'm going to do it quadrant by considering the graph quadrant by quadrant. Okay, so in the first quadrant, the angle varies, in the polar plane, the angle varies between 0 and pi over 2. So let's look back at the rectangular plane, the graph in the rectangular plane, where theta varies between 0 and pi over 2. Theta varying between 0 and pi over 2 corresponds to quadrant 1 in the polar plane. I might as well continue this. As theta varies between pi over 2 and pi in the polar plane, we look at we get the second quadrant in the polar plane. In quadrant 3, theta varies between pi and 3 pi over 2. And finally, as theta varies between 3 pi over 2 and 2 pi, we get a graph in the polar plane in the fourth quadrant. So let's look back in the first quadrant in the rectangular version of our curve. As theta varies between 0 and pi over 2, the r values vary from 0 and get bigger and bigger and bigger and bigger until they reach an r value of 1. So on the polar plane, these little red arrows that are increasing in length from 0 to 1 get put coming out of the origin. So let's say at pi over 2, this is an r value of 1. And at 0, the r value is 0. So as theta varies between 0 and pi over 2, those little red arrows vary in size from 0 and get bigger and bigger and bigger and bigger until they reach a length of 1. So those little red arrows that I've just drawn in the polar plane are the arrows that were going straight up and down, or straight up in the graph of the rectangular version of the curve. And similarly, in quadrant 2, as theta varies between pi over 2 and pi, the r values on a rectangular graph decrease in value from 1 and get smaller and smaller and smaller and smaller until they reach an r value of 0. So those little red arrows we're going to graph in our polar plane, but they're going to shoot out from the origin. So those little green arrows then are put in the polar plane in quadrant 2, and they decrease from 1 to 0. Smaller, 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 smaller to 0. It's not really showing up very well, but if we were to connect the arrows together, we would get something like this. Okay, now just because it looks almost circular the way I've drawn it doesn't mean that our actual curve is a circle. This happens to be a circle, but most graphs in polar form don't represent circles, even though they do represent closed curves. So remember that in polar form, curves in polar form tend to have loops in them, to loop around and around multiple times. Sometimes they look like figure eights, sometimes they look like clovers, sometimes they look like heart-shaped curves, and so forth. So let's continue on with this graph. We've only looked at theta varying between 0 and pi. let's see what happens as theta varies between pi and 3 pi over 2 in the third quadrant. So as theta varies between pi and 3 pi over 2, the r values continue to decrease from 0 and get smaller and smaller and smaller. They continue to decrease. They're becoming negative now and reach a value of -1 at 3 pi over 2. So this means something pretty significant in terms of the graph of our function. As theta varies between pi and 3 pi over 2 in the polar plane, that puts us back into quadrant 3. But the r values are negative. Remember, if the angles are in quadrant 3 and the r values are negative, then the actual points lie across the origin in the opposite quadrant, so in quadrant 1. So if we were to put those little blue arrows into the graph, what we'd be getting is those little blue arrows would exactly line up with the red arrows that were in quadrant 1 before. So as we move through quadrant 3, we trace out the portion of the circle again in quadrant 1. So we're really just overwriting or tracing over the same portion of the circle that we looked at in quadrant 1 when we consider our angles in quadrant 1. And finally, as theta varies between 3 pi over 2 and 2 pi, the r values are again negative. And I'm going to plot those in, let's say black. The r values, as we move through the angles in quadrant 4, from 3 pi over 2 to 2 pi, the r values increase then from -1 back to 0, from -1 back to 0. That puts us again in the opposite quadrant of quadrant 4. That puts us in quadrant 2. That means we're tracing out the same portion of the circle that we traced out in quadrant 2 earlier. We're retracing it with those negative r values. So as we go from 0 to pi, we trace out the entire circle. As we go from pi to 2 pi, we trace out the circle again. So the upshot of all this is that the circle, this curve, is traced out. To trace out this curve, we don't need the angle theta to vary between 0 and 2 pi. We only need the angle to vary between 0 and pi. This is very important in terms of finding areas. The limits of integration correspond to the values of theta that are required to trace out whatever portion of the curve is necessary for our area. And it's very common for students to say that we integrate from 0 to 2 pi, where in fact we only integrate from 0 to pi. So let's actually do that. The problem was to find the area. The area is the integral of 1/2 r squared d theta. 1/2 r equals sine of theta. So 1/2 sine of theta squared d theta. And theta varies between 0, not in 2 pi, but 0 and 1 pi. If we were to integrate between 0 and 2 pi, we would pick up too much area. We would pick up twice the area of this circle. In fact, I remember I said I wasn't going to evaluate any more integrals, but I want to evaluate this integral. Just to give you one more kind of review example. So this becomes the integral from 0 to 2 pi of 1/2. Now, to integrate sine squared, we use the power reducing formula that says 1/2 times 1 minus cosine of 2 theta. Okay, the power reducing formula for sine squared is 1/2 times 1 minus cosine of 2 theta. I distributed the 1/2. So if we factor out another 1/2 and factor that out of the integral sign, we're looking at the integral of, or rather 1/4 times the integral from 0 to pi, again, not 0 to 2 pi, 0 to 1 pi, 1 minus cosine of 2 theta with respect to theta. Continuing, the antiderivative of 1 is theta, antiderivative of cosine is sine, but over 2. So 1/2 sine of 2 theta. That factor of 1/2 comes from the 2 theta. And just as before, we can't assume that this always happens, but just as in the previous integral, that we get no contribution from the sine term at either 0 and pi, because the sine of 2 pi, when we substitute 1 pi into the sine of 2 theta, is 0, and the sine of 0 is 0. And we get no contribution again from the lower limit, 0, for either of these terms. So we're looking at 1/4 times pi, or pi over 4. So this should correspond to the area of a circle. Excuse me. Our circle is a circle. The radius of the circle is not 1. The radius of the circle is 1/2. The tip of the circle that we've drawn hits the y-axis at 1, so its radius is 1/2. So to check, this area equals 1/2. Oops, that's not the area of a circle. The area of a circle is pi r squared. So pi times 1/2 squared, or pi over 4. Pi over 4 square units, just as we figured out by using calculus. Our next example is going to involve finding the area captured between two polar curves. So we're going to need to increase our formulas a little bit. What we're going to do now is something very similar to what we did in Calc 1 after we looked at our first area problem. In Calc 1, if you'll recall, the first application of the definite integral was to find the area bounded above by a function and below by the x-axis between 2 points A and B. Okay, so this is just a review of what we did in Calc 1 to try to motivate our formula for today. In Calc 1, we determined that the area was equal to the integral from a to b of f of x dx. Then the very next thing we did is we increased or changed the problem a little bit by looking at finding the area captured between two functions. Suppose we have a function f of x on top and some other function g of x on the bottom, and we're interested in finding the area between these two curves, between 2 points A and B along the x-axis. The formula that we got was real simple. Let's say y equals f of x for our first function, or the function on top, if you will. We use the same terminology we did in Calc 1. And y equals g of x is the function on the bottom. We determined that the area between these two curves, between a and b, was the integral of the function on the top minus the function on the bottom with respect to x. In fact, in my Calculus 1 classes, I often write the formula as y top minus y bottom dx is kind of an easy device for remembering. So we're going to do a similar thing now, but in the polar form. We're still interested in the area captured between two curves, but the curves are given in polar form. Remember, curves in polar form aren't formed by taking an x horizontally and graphing a corresponding y vertically. The curves in polar form are obtained by looking at r values as they shoot out from the origin. So let's say we're looking at finding the area between two polar curves. Let's see here. Between two polar curves, as theta varies between two constants, theta equals alpha and theta equals beta. The corresponding formula for the area is actually very simple. It's very, very simple. And it actually corresponds to the y top minus y bottom formula that we learned in Calc 1. Again, imagine filling this region between the two curves with an infinite number of little areas, or areas of little circular sectors. Okay, so here's the area captured between two circles. Okay, so let's say the first curve, the curve on the inside, that means closer to the origin, is R1, and that R1 is g of theta, and the curve on the outside is R2 equals, let's say, f of theta. Now, if we didn't have the curve R1 in the picture, we would have the same problem as we did earlier. If we didn't have R1 as a sort of inner curve, we would be looking at the total area from the origin out to R2, and that would look like the integral from alpha to beta of 1/2 r squared f of theta squared d theta. Okay, now to actually find the area between the two curves, and here's where it's really simple. The development of this formula is very simple. We subtract out the area captured between the origin and R1. The area captured between the origin and R1 by our initial formula earlier is the integral from alpha to beta of 1/2 g of theta, the inner function squared, d theta. Well, we can combine these two integrals. We can combine them into one integral. So the area captured between two curves, an inner curve and an outer curve, is nothing more than the integral of 1/2 of the curve on the outside squared minus the equation of the curve on the inside squared with respect to theta. I think a nice simple formula, a simpler formula, might be to think about it as the integral from alpha to beta of 1/2, let's say, r outside squared minus r, the inside r, inner or inside squared d theta. So take a look at the simplified formula from Calc 1 in, let's say, green. And let me see if I can get that upper limit of integration to also be green. There we are. And let's compare that to our formula also in green for the area captured between two polar curves. And look at the similarity. In Calc 1, the area between two curves, integral of y top minus y bottom dx, sort of like y outer and minus y inner, outer being farthest from the x-axis, inner being closest to the x-axis. And here, integral 1/2 r outside squared minus r inside squared d theta. So the formula is very, very simple, and it corresponds almost identically to the formula in Calc 1 for the area captured between two curves. Okay, so let's take a look at an example. This one, again, the most difficult part of this example is going to be actually coming up with the graphs from trig of the functions. So here's our example. I want to find the area that lies outside one curve and inside another curve. Okay, so in other words, find the area in the polar plane captured between two curves. But I'm going to state it the way I just did. I want to find the area that lies outside one curve. Let's say the curve is r equals sine of 2 theta. We'll spend some quality time on graphing that in a minute. I think I might have this backwards, not outside. I want it inside. I want it inside this curve and outside another curve. The second curve is one we've already visited, and outside r equals sine of theta, the circle we just graphed. But I want only the portion of this area within the first quadrant. This will make sense in a minute. So within the first quadrant. Okay. Again, this being an area only in the first quadrant, that idea will become real clear in a minute. So let's graph our new function. Let's graph r equals sine of 2 theta. This one is a bit rough. Once again, the calculator will produce these images very nicely, but they don't reveal, the graphing calculator doesn't reveal very well the angles that appear that we need to pick off of our graphs. So you might want to combine using your graphing calculator with graphing by hand. It might be helpful. Okay, so let's graph this. In order to graph, I'm going to use the same technique that I used. I'm going to graph the r equals sine of 2 theta first in the rectangular plane. Okay. Well, r equals sine of 2 theta, it has a different period than r equals sine of 1 theta. The period of r equals sine of 2 theta is 2 pi divided by the coefficient of theta. To remind you, that's how we figure out the period of a sine or cosine. We take 2 pi and divide by the coefficient of theta. So the period of this function is only pi as opposed to 2 pi. So let's graph a period of this function. So one period of this function looks like this approximately. Okay, and it's between 0 and pi. So this is pi over 2. Reaches maximum at pi over 4. This is 3 pi over 4. And the amplitude is 1, so it goes up to 1, down to -1, and so forth. Okay. All right, so let's transform this graph of r equals the sine of 2 theta graphed in the rectangular r versus theta plane. Let's graph this in the polar plane now. Okay, this is a little tricky. So let me draw our axis in the polar plane. Here we go. That'll be enough. I'm going to draw a little circle. This circle is not part of our graph. The circle is only here to help me keep my graph contained where it should be. Give me a second here. I'm drawing a little circle. This circle is not the graph of our function. Also, not a very nice circle. Okay. In fact, it's a terrible circle. Give me a second here. I guess I could edit the video, edit this section out, but I'm not going to. No. Okay. Bear with me. Okay. Okay. All right. Okay, almost there. That's as good as I'm going to get for now. Okay, so we're gonna graph the corresponding graph that we have above, but we're going to graph it in the polar plane now. So we're going to look quadrant by quadrant, just as we did before. So look back up at the graph in the rectangular form. The graph in the rectangular form, we're going to look at between 0 and pi over 2. That corresponds to, in the polar plane, quadrant 1. So quadrant 1 will correspond to the graph in the rectangular plane as the graph between 0 and pi over 2. And I'm going to put those little arrows in. Look what happens as we move through quadrant 1. As theta varies between 0 and pi over 4, the r values vary between 0 and 1, and then they come back to 0, finishing out quadrant 1. The r values go from 0 to 1 and back to 0, all in quadrant 1. So what that means is this. I need to place all those little red arrows into the graph in the polar plane, but all in quadrant 1. As theta varies between 0 and pi over 4, the r values vary between 0 and 1. Let's say this r value I'm drawing now is 1. So the r values are varying from 0 to 1. So the r values are 0 when theta equals 0, and they get bigger and bigger and bigger and bigger and bigger until they reach an r value of 1 at pi over 4. Then, as theta goes from pi over 4 to pi over 2, the r values decrease from 1 and get smaller and smaller and smaller and smaller and smaller and smaller until they reach a value of 0. So in quadrant 1, we're picking up a graph of a curve that looks like this. So let's say back in the rectangular plane, the portion of the sine graph that goes from 0 to 1 we'll label as 1. That corresponds in the polar plane to this little portion. The graph in the rectangular plane that goes from 1 to 0 we'll label as part 2. That corresponds to part 2 in the polar plane. So we're getting one complete loop in quadrant 1. Let's take a look at the angles in quadrant 2. In quadrant 2, the angles vary between pi over 2 and pi. And I'm drawing a line through quadrant 2 and quadrant 4 on purpose. I think you'll see why in a minute. So, in quadrant 2, the angles vary between pi over 2 and pi. So in the rectangular plane, those correspond to R values that go from 0 to -1, and then from -1 back to 0. All of this occurs in the polar plane in quadrant 2. Quadrant 2. So in the polar plane, the R values need to go from 0 to -1 and back to 0. If they went from 0 to +1 and back to 0, we would get a graph in the polar plane that looked like this, from 0 to 1 back to 0. But that's not what happens. As theta varies between 0 and pi, the R values vary from 0 to -1 back to 0. So specifically, if 3 in the rectangular plane, if that little 3 that I'm going to change into a better looking 3, if 3 in the rectangular plane corresponds to the graph between pi over 2 and 3 pi over 4 in the rectangular plane, in the polar plane it corresponds to this little portion. If 4 corresponds to the portion of the graph in the rectangular plane between 3 pi over 4 and pi, then in the polar plane we get this portion. If we were to continue to look at the next period of the sine graph, the sine of 2 theta, in the in the rectangular plane, we would get another portion of the graph of this sort of rose or flower or clover, whatever, in the polar plane, and it would look like this. If we were to continue still, we would get the last leaf of our flower. So in this case, we get what's often referred to as a 4-petaled rose as a polar graph. So the graph of R equals sine of 2 theta is this little rose-like figure. So what I'm interested in is the area that is inside the rose, but outside of that circle we drew earlier, R equals sine of theta, but only that portion of the area between these two curves that lies in quadrant 1. I'm going to draw the initial rose, or initial circle, R equals sine of theta, onto our drawing of our 4-leafed rose or 4-leafed clover, whatever, and then we'll clean up the drawing a little bit to do our area. So if we were to draw the original curve we had before, R equals sine of theta, right onto our picture of the rose, we would see this. So what we're interested in is the area that is inside the rose but outside the green circle. So what we're interested in, and I think this is going to look really cluttered up, but we'll clean it up if it turns out bad. What we're interested in finding is this area that I'm shading in blue. And the shading might not turn out very nice, but we'll clean up the graph. We're interested in the area that's inside the rose but outside the green circle, but only that portion in the first quadrant. We're interested in this area in blue, right here. Okay, so let's do it. We have a formula now. We developed a formula for the area inside one curve and outside another. It's the integral of 1/2 of the r on the outside squared minus r on the inside squared d theta. Let's redraw. Let's take a look at redrawing just that portion of the area that we're interested in. Okay, so give me a second to do that. I might be able to get a decent drawing of it here. Okay, we're only looking at that portion of the area in blue above in the first quadrant. This circle, this portion of the circle is just for me to keep my graph contained. It's part of our graph. And again, just as before, it doesn't look like a circle either. It's all right. So here is our circle, r equals sine of theta. And here is the rows, r equals sine 2 theta. And I guess I didn't really need that initial circle that I drew. It's really going to get in the way. So what I'm doing is I'm using the eraser feature on my smart pen. I think my smart pen is smarter than I am. Okay. So what we're interested in is the area that is inside the rows and outside the circle. Now, we're gonna use the formula that we just developed. That the area equals the integral from alpha to beta of 1/2. Let's clean up that 1/2 a little bit. Area from alpha to beta of 1/2 r outside squared minus r inside squared d theta. In order to figure out what's outside and inside, I recommend you draw one typical circular sector through your region. One typical circular sector in your region. And with that one typical circular sector, you can kind of see, you shade in the area that's picked up from that circular sector, you can kind of see which function is on the outside and which function is on the inside for the integral. Okay, it looks like r on the outside is the rows, r on the inside is the circle, even though the problem stated it that way. So the area then is the integral of 1/2. R on the outside is the rows. The rows is sine of 2 theta squared minus r on the inside squared. The inside squared is the circle. R equals sine of theta squared. Integrating that with respect to theta. As theta varies to produce the blue common region. Now, there's a little bit of a difficulty here that we have to contend with. The lower limit of integration is 0. And you can see that as our area begins, theta for both curves is 0. But where we stop this integration is not immediately clear. Where we stop this integration is the theta value that corresponds to this dotted green line. I need to know where both these curves intersect. So what I'm going to do is I'm going to use my trigonometry to do that. These two curves intersect when the two functions are equal to each other. When the rows, sine of 2 theta, equals the r value for the circle. So I have to solve a trig equation. Okay, so that says that the sine of 2 theta minus the sine of 1 theta equals 0. double angle formula for sine of theta says sine of 2 theta says sine of 2 theta equals 2 sine of theta cosine of theta minus sine of theta equals 0. Factoring out the sine of theta, I realize I'm running out of room here. I think this will work out nice though. We'll find out. 2 cosine theta minus 1 equals 0. I might be able to squeeze a little more in here. So this says that the sine of theta equals 0, or the cosine of theta equals 1/2. And we solve these two equations. So sine of theta equals 0 when theta equals 0, and the cosine of theta equals 1/2 when theta equals, remember, unit circle, pi over 3. That pi over 3 is our upper limit of integration. So to find the limits of integration, we really need to have a hand drawing of this. Although we might be able to get away with a combination of graphing the graph using the graphing calculator, and then maybe using some trig to solve the trig equation to get the angle of intersection, or yeah, the angle where we have the intersection of the two curves. Okay, let's do one more example to end this section. To end this section, I'm going to consider the same two curves. I'm interested in changing the wording though. In the previous example, I wanted the area that was inside the rows and outside the circle. For our last example, I want to find the area in the first quadrant, let's say, that's enclosed by both curves. Enclosed by both curves. And there's a difference. Okay, the difference will become clear in a minute. So here's our statement of the problem. For our last example for this section, I want to find the area enclosed by both the curves, by r equals sine of 2 theta and r equals sine of 1 theta, the rows and the circle. Okay, so here's a quick drawing of our region again. I'm interested in the area enclosed by both curves. Let's draw that again. Here's r equals sine of theta. Here is r equals sine of 2 theta. I'm getting a little better at this. Previously, I wanted the area inside rows, outside circle. Now I want the area that's enclosed by both. I want the area that's inside the circle at the same time, I'm sorry, inside the rows at the same time inside the circle. So I've drawn two arrows, nervously, that indicate the area that I'm looking for. So let's find that area. This area, to find this area, we don't use the formula for the area between two curves, even though it looks like maybe we're supposed to use that formula. It's really not. Let me try this again. That'll work. Okay. The common angle of intersection that we had with the green dotted line before, I'm going to put in. This is theta equals pi over 3. And notice that this area, the area we're interested in, can be broken down into two pieces. The area that's inside the circle, and I'm lining in here, plus the area that's inside the rows, the little red portion that I'm lining off here. Each of those areas, the green area and the red area, are not areas captured between two curves. They're area captured between captured by one curve. Okay, specifically, let's take a look at the green area. The green area is the area captured, if I draw a typical circular sector, it's an area captured within one curve. And similarly, the red area above this is the area captured within one curve. So the total area then, the total area is the area enclosed by the circular part, the r equals sine theta, the green area. And that area is the integral from 0 to pi over 3 of 1/2 the r value for the circle squared, that's the green area, plus the area of the red portion. In the red portion, theta is going to pick up where we left off in the green portion. Theta goes from pi over 3 to where the rose disappears, the theta value where the rose disappears. The rose disappears at the last value of theta in quadrant 1, which is that ends quadrant 1, which is pi over 2. The r value in that little area is r equals sine of 2 theta, so it's the rose r value squared d theta. Then we evaluate that integral. Okay, and that ends the lecture for sections 10.3 and 10.4. Feel free to dig into homework whenever you're ready, and I look forward to talking with you again.